Hi there, and welcome to Raylene Math. Let's take a look at one-dimensional motion as an example of rate of change. Now, rate of change we know means slope, and if we have a position function, like we do, measured in feet, then the slope of position is another vector, and that vector is velocity. Now, I don't know exactly what this graph looks like, but let me just imagine it looks something like this. If I find the slope through 2 points, then I'm finding a secant slope, or the average rate of change. And if I zoom in at a given point, say this one here, and draw a tangent line, then I'm coming up with the instantaneous rate of change at a single instant or time value. Another name for the instantaneous rate of change is the derivative. So in part A, we are asked to find the velocity at time t. Because it says the word at here, we know that we are at a single point in time, at an instant. And so we are looking for the instantaneous velocity as opposed to the average velocity between two time values, some time interval. And so the velocity is going to be at time t, the instantaneous rate of change, or the derivative of the position with respect to time. So we get 3t squared minus 24t plus 45. Now right away I see a common factor of 3, and I'm inclined to factor that out, just to see if we might be able to take advantage of some factoring or some algebra later on. And it does in fact factor into two linear factors, product of two linear factors times the 3. Don't divide through by that 3. We're not automatically setting the right hand or the left hand side equal to 0, so we're not automatically eliminating that 3. That 3 factor is necessary for calculating the velocity properly. So there's my answer. I'm not going to fit it in the box. Now the question is, what's the velocity after 5 seconds? It's simply a matter of evaluating, but I notice that 5 is one of the zeros, and so 5 minus 3 times 5 minus 5 gives me 0 feet per second. And then when is the particle at rest? The particle at rest is just another way of saying velocity is equal to 0, so now we're working backwards, and it is practical that I have my factored form, because from here I can see my two my two time values that produce a velocity of 0 are either t equals 3 seconds or t equal to 5 seconds. So you can put those in here. Another part of this question that I'm looking at is asking for the acceleration at time t, which is another indication of an instantaneous rate of change. And velocity is the rate of change, or the slope of, rather the acceleration is the rate of change of the velocity time graph. Now I know I have a velocity graph already, which is a quadratic, so I'm going to plot that quadratic velocity, which is measured in feet per second, versus time measured in seconds. And I have a concave up parabola with two time intercepts at 3 or 5. And so I know that I have an axis of symmetry which is somewhere along t equal to 4, and I could substitute 4 in for the t. 4 minus 3 is 1, 4 minus 5 is negative 1, times 3 is going to give me negative 3. So at 4 seconds I have a velocity of negative 3, and at 3 and 5 seconds I have a velocity of 0 and a concave up parabola. Now I haven't sketched it very well, but certainly I'm going to have a velocity intercept over here at 45. And so I'll just tidy that up and imagine that somewhere along here I have a velocity intercept at 0.45. Now this is not necessary for coming up with the acceleration, but it is helpful for me to understand that if I want to find the acceleration at a single instant in time, and then at 5 seconds, that the acceleration is the instantaneous rate of change, or the derivative of the velocity graph. And so later on I'm going to find the velocity at 5, the acceleration at 5, so I'm going to zoom in and imagine a tangent line. The slope of that tangent line to t equal to 5, to the curve at t equal to 5, is my acceleration at 5. So by looking at my picture, I should get a positive value for acceleration here at 5 seconds. Okay, so let's come up with the acceleration, which we know is the slope of velocity, and in this case it's the instantaneous rate of change of velocity. So it's dv by dt, or it's the second derivative of position, so it's f double prime of t. Going back to my expanded version of velocity then, I have that my acceleration is going to be given by 6t minus 24. So that's my function a linear function now for acceleration, and I could graph that acceleration graph if I wanted to, with a negative 24 initial acceleration value, rise 6, run 1, and I will cross at t equal to 4 here on my acceleration feet per second squared versus time graph. And then to substitute 5 into the acceleration graph, I can plug in 5 on the acceleration graph directly and get a height of 6 times 5 is 30 minus 24 is 6, which is the same as saying the slope of this purple tangent line is 6 feet per second squared. Now, of course, you don't have to draw these graphs, but doing so allows us to see a lot of the connections between them. And here I have some graphs a little bit more in detail. We see the feet graph. Now, the position graph wasn't really easy to see, so if I go back, I just made something up here. I knew it was a cubic, so I knew the end behavior that it would have, but I didn't know exactly where it would turn around. I can see from the factoring very easily. I can factor out a t, and I can see that I'm going to have at least a root at t equal to 0. And so my graph actually should be crossing through 0, 0 for the position graph. But the rest of it I'm not really sure about. So let's not worry about where this graph comes from just for now, and let's fill in some other connections that we see about the graph. First of all, in the velocity graph, we know that at time 3, the velocity changes from a positive value, meaning above the horizontal axis, to negative velocity values, which means that the position changes from increasing to decreasing. And that means that the direction of the particle is changing from an increasing position, or moving to the right, to a decreasing of position, which is moving to the left. And so we have that at time equal to 3, the position is increasing, and then at t equal to 3, the position starts to decrease. So we know that we've reached some maximum position. If we consider that the particle is moving along a horizontal line, because we're only in one dimension, then we are starting at some initial position, which according to this equation here, at time 0, the initial position is going to be 0. So the particle starts at position 0 and then increases for 3 seconds, meaning goes to the right for 3 seconds. And then at time equal to 5, we see that the velocity is changing from being a negative velocity value below the horizontal axis to above the horizontal axis. So the velocity changes from being a negative quantity to a positive quantity, and meanwhile, the position is changing from decreasing to increasing, which means that the direction is changing from left to right. And so we see that at time equal to 5, the particle is going to have another turn or change of direction. The particle is decreasing, and then after 5, the particle's position, not just the particle, is increasing. And so while we may not see exactly how high that max and how low that min point are, meaning how far to the left it goes, maybe it goes really far to the left, maybe it doesn't go so far to the left, we're not exactly sure about that. But we do know that for a few seconds this particle is going to go to the left. Let me just clarify this. This is from t equals 0 until t equals 3, and then the particle is going to go from that max x coordinate to the left a little bit, and that's from t equals 3 until t equals 5, and then after that time the particle is going to go to the right again. And so we see that the particle goes right, left, and right. Okay, this is interesting and useful then because we are asking questions, when is the particle moving in the positive direction? One of the challenges of a question like this is to interpret the words into equations and inequalities. So particle moving in the positive direction, we can say is moving to the right. Positive direction implies moving to the right. And we want to change these words into something to do with position, velocity, or acceleration. And moving to the right means that the position, the horizontal position, increases. And if the horizontal position is increasing, then the velocity is positive. One of the pitfalls here is that we are often a bit sloppy and we say it increases, so it is positive. But obviously those two different its. One is the position and one is the velocity. So if we avoid using the word it, we can kind of keep all of our quantities and our graphs clear. And so the velocity being positive means we can go back and look at our velocity graph, which was some kind of concave up parabola with intercepts along the horizontal axis at 3 and 5. So this is our velocity versus time graph. And so for the velocity to be positive, we're really looking to solve an inequality. We want to solve for the velocity greater than 0 such that, or solve for rather a quantity. We want to solve for when. So we want to solve for t time such that the velocity is greater than 0. So I'm going to rewrite that velocity as a red function, and that 0 is going to be another color graph, and I'm going to look at this as some y equal to a velocity function and some y equal to 0. So y equal to 0 is the horizontal axis. And when we are solving inequalities graphically, we think of which color graph we want to be higher or lower. So according to this statement here, we want the red graph to be higher than the green graph. Alternatively, we want the green graph to be lower than the red graph. And we know that the red graph is going to be higher for all of these values. And so I think we had a time domain of 0. Yeah, it says that the time is greater than or equal to 0. And so for those time values, we see that from 0 until 3 seconds, the velocity is positive, or from 5 onwards. So the solution is going to be the set of time values contained from 0 to 3, not including 3, because that's when the velocity equals 0. But at time 0, the velocity is positive, so we include it. Union from 5 onwards to infinity. And so this is consistent with a set of time values that makes the velocity positive, and therefore the particle moves to the right. The next question we're asked is to find the total distance traveled during the first 7 seconds. Now there's many approaches to this question, and if you know about accumulating speed, then you can calculate distance, but that requires integration. So I wonder if there's a way we can look at it without integration. So we consider that for the first 3 seconds the particle moves to the right. Let's call this point A and point B. And then that's t equal to 0 and t equal to 3. And then from that point B it moves to the left. Let's call that a new point C, and that corresponds with t equal to 5. And then after t equal to 5 the particle moves to the right. So if we're going to chop it off at 7 seconds, maybe that's point D corresponding with t equal to 7. So one question you might ask is, how do we know that the particle didn't go further to the left? We don't, but this is just a representation for now of the directions. So from this in mind, we know that the particle is going to have a certain distance, which is really the distance from the location at time A until the location at time D, and it's going to be broken up into 3 segments where the direction changes. So we always need to kind of consider where the direction of the motion changes when we want to accumulate the travel, the distance. So we have the distance from point A to B, or from time A to B, added to the distance traveled from time B to C, added to the distance traveled from C to D. And now we can see that distance is related to the displacement. If there's no change in direction, then distance is the absolute value of the displacement in between changes of direction. So the change of direction, or the displacement rather, is a change in x. And we're going to have a displacement from A to B, and then if we take the absolute value of that, that's the same as the distance from A to B. And then we have the absolute value of the displacement from B to C, and the absolute value of the displacement from C to D. And from here we notice that the displacement from A to B is a positive displacement, and therefore the absolute value signs are not necessary. But the displacement from B to C is a negative displacement, and so the absolute value of negative stuff has to become positive, so the absolute value will change the sign of stuff to remove the absolute value. So we get negative delta x from B to C. Lastly, the displacement from point C to D is a positive displacement going to the right, and so the absolute values are not necessary and we can just remove them. The absolute values do absolutely nothing. And now recalling our definition of displacement or change, it's going to be the final minus the initial. So this is x at B minus x at C, x at A. And we have minus x final minus x initial, and then we have x final minus x initial. And so each of these is a value of x, or s as it was called in the original problem. And so we can calculate that using our function s, or x, is equal to f of t, which was the original cubic function. So there's no need for integration because we're really just talking about position values, but recognizing that there's a change in position and the change of position could be positive or negative on each individual segment. And I think it was minus 12t squared plus 45t. So from here, we can recognize that point B refers to time 3, and so I'm going to call this xb the same as f of 3 minus xa, which is f of 0. And then minus xc, which is f of 5, and minus a negative is a plus f at point B, which is time 3. And then x at point D, or time D, is going to be f of 7 minus f for point C, which is at 5. So I'm just going to collect some of these. I remember that my position at time 0 was 0, so that one is 0. And I'm going to get 2 f of 3's plus an f of 7 minus 2 f of 5's, and it would have been minus f of 0, but that value is 0. So this is really an algebra question or an evaluation question. We can use a graphing problem or program to help us work that out a little bit more simply. So let's take a look. If we define our function f of t to be t cubed minus 12t squared plus 45t, and then we can evaluate our different function values. Let's see if I can recall it quickly. 3, 7, and 5. Let's see if I can do it. So we have 2 f of 3 minus f of minus 2 f of 5 plus f of 7. Let's just double check that. Yep, minus 2 f of 5 plus 1 f of 7. And so this value is 78. And that makes sense, at least in that it's positive, because we are getting a distance, so it had better be a positive value. And so that's one way without integration that we can interpret this total distance from the given information. Another common question for particle motion problems is, when is the particle speeding up or slowing down? And so it is useful to have some kind of template to rewrite the word problem, such as solve for something given some information, or such that. We might write it that way. Given or such that something is true. So the first part of the question about speeding up is saying to solve for when, which means time, solve for t, such that the particle is speeding up. So that's another way of saying that speed increases. Now we need to relate speed to one of our motion quantities of position, velocity, or acceleration. Position, velocity, and acceleration all involve direction, whereas speed doesn't. Speed is just a magnitude. And if you know the units of speed, feet per second, then you'll know that it is the magnitude of the velocity function. So if we take a look at our velocity function, we can come up with a graph of it. And from that graph of velocity, we can do a transformation to come up with the speed. If we apply absolute value or partial vertical reflection, then any part of the velocity graph that lies below the horizontal axis gets reflected up. And this is going to give us the speed graph. So we have our speed graph like this. Now I've chopped this off at time 7, but that graph can actually continue on. This one is stopping at 0 because we had a time domain given to us. So we have some indication of this point, which was the vertex. I think we found out it earlier to be 4, -3. And so when we do a partial vertical reflection, that velocity value becomes the speed value of just 3 at time 4. And so the question of when is the particle speeding up, which is the same as when is the speed graph increasing. So if we look at the speed graph increasing, we can see from 3 until 4, and then 5 until infinity. And so speed increases is equivalent to saying the absolute value of the velocity graph increases, and from the velocity graph we get the speed graph, which tells us that time is contained from 3 until 4, union 5 until infinity. The second question is a variation on that and asks when is the speed decreasing or slowing down. The particle slowing down is the same as speed decreasing, which is solving for the absolute value of velocity to be decreasing. And the time values for that belong with 0 until 3, and then from 4 until 5. So we can see that the graphs really make our understanding of these motion quantities, the position, the velocity, the speed, and the acceleration, much easier to understand. So hopefully you'll consider drawing some graphs and combine it with the algebra or the derivatives when you're looking at one-dimensional motion and rates of change. Thanks for checking out Raylene Math.